Hello, my name is Dawei, and today I'll be presenting my project, the Interpretability of Machine Learning. I have stored my project in this GitHub repository, which could be easily accessed by this link over here. So starting off, it is important for us to consider the interpretability of machine learning algorithms, because it is important that we as humans understand the model before we implement it. And for this project, we will explore one specific avenue of machine learning interpretability and claim that a model is interpretable if a user could adequately discern each feature, the weight of each feature that contribute to the final output. Of course, we know that there exist other model-agnostic methods that would accurately calculate the weight for us, such as partial dependency plots and Shapley values. But we know that these methods are computationally expensive. So the point of this project is for us to develop a new model-agnostic method based on the production of random values that would allow us to ascertain the approximations to the weights in faster time. Now, if you scroll down to my project documentation, I have included some examples on how my code should be run. First of all, be sure to import this ran method file because it contains all the functions associated with RandomGen. So first, I would import this table from this file over here, and I would put it through this function createGraph, which takes the input, the ideal outputs, the list of all the features I wish to display on the graph, the number of random consecutive changes I wish to be made to each feature, the model I'll be accessing, and whether or not I want this graph to be smooth, which I will come back to later. So after running it through this function over here, I would output this graph. Each line in this graph would represent a feature. So this model would access the features of frequency, angle attack, core length, and the output would be noise. Yes. So if you look at this graph over here, the x-axis would represent the number of consecutive random changes I would be making to each feature. And the y-axis over here will represent the deviation from the initial output. And this chart right here just includes the slope of each feature line that's present on the graph. So scrolling down, you have the option of whether or not you like your graph to be smooth. Quite simply, smoothing just smooths out each line by averaging each point with its neighbors, right? So the left graph is without smoothing, and the right graph is with smoothing. Going back to this graphic over here, we have shown that frequency has a much more significant weight than the other variables because with each consecutive change to data in the feature, we have shown that it deviates from the initial output at a much faster rate than the other variables. Moving on, I have also included 7 additional test cases in this Jupyter Notebook file that I have in my GitHub repository. And these 7 cases test both ML tasks of regression and classification. So looking at this first test case, linear regression of hours.csv, I import this table and I run it through createGraph, which gives me this graphic right here, which shows that registered is the variable that has the most significant weight. And we could confirm this with Shapley values over here, and it does indeed show that registered has a much more significant weight than the other variables. One important thing to note here is that you should always run this graph multiple times because it is based on the generation of random values. So it's possible that you might have a graph 1 in 10 times that's very extreme. So moving on, we have included a second test case, decision tree of hours.csv, which produces this graphic right here, which is not as nice as the first one, but indeed it shows that registered is the most significant variable, which we could confirm with Shapley values that show indeed registered is much more significant than the other variables. And we could also use this method to assess black box method, such as random forest. And I will produce this graphic over here, which does show that registered is the most significant variable. Now, if you think that RandomGen is not capable of finding more than one variable with significant weights, I have included a second data set, which should have multiple significant inputs. So after running this create graph function, I have this graph over here, which shows that frequency has the most significant weight, followed by chord length and angle attack. And I want to confirm this with Shapley values, which indeed show that frequency has the most significant weight, followed by chord length and angle attack. And a very important thing to note here, I've noticed, is that the difference between each of these slopes right here is not according to scale. This shows that frequency is much more significant than chord length, which we have shown in Shapley values to not necessarily be the case. Now moving on to random forest regressor of the same dataset, we see here that after running create graph on random forest, we get a graph that looks like this. Compared with the previous graph over here, these lines are obviously not smooth, and this is probably the case because with each random change in the feature, it's much harder to access the exact deviation from the initial output, and it's much less consistent. So I have included a way to smooth out this graph, which I did right here, and this is purely for aesthetic purposes. So moving on to logistic regression of happiness survey, this data set is actually a classification machine learning task. So this data set basically includes a bunch of inputs, and the output is yes or no, is this person happy or not? And looking at the graph right here, we see the same pattern as the previous few graphs. So this indicates that RandomGen also works well with classification, and it produces the following variables with these following slopes, which if we match it up to Shapley values, it matches almost exactly. Like one is x1, 2 is x6, one is x1, 2 is x6, but the dot value is slightly off, x5 and x4. So to repeat my previous point, this method is not exact, but it gives a pretty good approximation. Finally, we have our seventh test case, the random forest regressor of the same dataset, happiness survey. So after running random forest, I get this graph right here. And this graph, while not exactly the same as the Shapley value analysis, is pretty close. You see here that the variable with the top weights is x1 and x3. And so it is here, but in a different order. And one way we could assess the accuracy of RandomGen is quite simple. I have done it for some test cases here. For example, in test case 4, I assess the RandomGen accuracy. What this function does, accuracy score, is that it runs create graph multiple times, 3 times to be exact, and checks how many times this function indicates frequency and chord length as the variable with the most significant weights, right? So here we have a RandomGen accuracy of 1, which indicates that in 100% of cases, frequency and chord length are in the top 2 weights of each variable. To conclude my presentation, I just want to claim that RandomGen works the best with models that are good to begin with. So models whose output fits the ideal output very well. Because if it doesn't fit it very well, it'll be trivial to measure deviation with each consecutive random change from the initial output if the initial output itself is not very accurate to start with.